Gradient Boosting Neural Networks, GrowNet, Sarkhan Badirli, Department of Computer Science, Purdue University, Indiana, USA. Xuanqing Liu, Department of Computer Science, UCLA, California, USA. Zhengming Xing, LinkedIn, California, USA. Averdeep Paumik, Amazon, California, USA. Koa Doan, Department of Computer Science, Virginia Tech, Virginia, USA. Sathya S. Kirthi, LinkedIn, California, USA. Abstract. A novel gradient boosting framework is proposed where shallow neural networks are employed as weak learners. General loss functions are considered under this unified framework, with specific examples presented for classification, regression, and learning to rank. A fully corrective step is incorporated to remedy the pitfall of greedy function approximation of classic gradient boosting decision tree. The proposed model rendered outperforming results against state-of-the-art boosting methods in all three tasks on multiple datasets. An ablation study is performed to shed light on the effect of each model component and model hyperparameters. Introduction: AI and machine learning pervade every aspect of modern life, from email spam filtering and e-commerce to financial security and medical diagnostics. Deep learning in particular has been one of the key innovations that has truly pushed the boundary of science beyond what was considered feasible. However, in spite of its seemingly limitless possibilities, both in theory as well as demonstrated practice, developing tailor-made deep neural networks for new application areas remains notoriously difficult because of its inherent complexity. Designing architectures for any given application requires immense dexterity and often a lot of luck. The lack of an established paradigm for creating an application-specific DNN presents significant challenges to practitioners and often results in resorting to heuristics or even hacks. In this paper, we attempt to rectify this situation by introducing a novel paradigm that builds neural networks from the ground up layer by layer. Specifically, we use the idea of gradient boosting, which has a formidable reputation in machine learning for its capacity to incrementally build sophisticated models out of simpler components that can successfully be applied to the most complex learning tasks. Popular GBDT frameworks like XGBoost, LightGBM, and CatBoost use decision trees as weak learners and combine them using a gradient boosting framework to build complex models that are widely used in both academia and industry as a reliable workhorse for common tasks in a wide variety of domains. However, while useful in their own right, decision trees are not universally applicable, and there are many domains, especially involving structured data, where deep neural networks perform much better. In this paper, we combine the power of gradient boosting with the flexibility and versatility of neural networks and introduce a new modeling paradigm called GrowNet that can build up a DNN layer by layer. Instead of decision trees, we use shallow neural networks as our weak learners in a general gradient boosting framework that can be applied to a wide variety of tasks spanning classification, regression, and ranking. We introduce further innovations, like adding second-order statistics to the training process, and also including a global corrective step that has been shown, both in theory and in empirical evaluation, to provide performance lift and precise fine-tuning to the specific task at hand. Our specific contributions are summarized below. We propose a novel approach to combine the power of gradient boosting to incrementally build complex deep neural networks out of shallow components. We introduce a versatile framework that can readily be adapted for a diverse range of machine learning tasks in a wide variety of domains. We develop an off-the-shelf optimization algorithm that is faster and easier to train than traditional deep neural networks. We introduce training innovations including second-order statistics and global corrective steps that improve stability and allow finer-grained tuning of our models for specific tasks. We demonstrate the efficacy of our techniques using experimental evaluation and show superior results on multiple real datasets in 3 different machine learning tasks: classification, regression, and learning to rank. Related work. In this section, we briefly summarize the gradient boosting algorithms with decision trees and general boosting ensemble methods for training neural nets. Gradient boosting algorithms. Gradient boosting machine is a function estimation method using numerical optimization in the function space. Decision trees are the most common functions that are used in gradient boosting framework. In his seminal paper, Proposed Gradient Boosting Decision Trees, GBDT, where decision trees are trained in sequence, and each tree is modeled by fitting negative gradients. Unlike parameter estimation, function approximation cannot be solved by traditional optimization methods in Euclidean space. In recent years, there have been many implementations of GBDT in machine learning literature. Among these, used GBDT to perform learning to rank, did classification, and generalized GBDT for multitasking purposes. In particular, Scalable Framework have made it possible for data scientists to achieve state-of-the-art results on various industry-related machine learning problems. For that reason, we take XGBoost as our baseline. Unlike these GBDT methods, we propose gradient boosting neural network, where we train gradient boosting with shallow neural nets. Using neural nets as base learners also gives our method an edge over GBDT models, where we can correct each previous model after adding the new one, referred to as corrective step, in addition to the ability to propagate information from the previous predictors to the next ones. Boosted neural nets. Although weak learners like decision trees are popular in boosting and ensemble methods, there have been a substantial work done on combining neural nets with boosting ensemble methods for better performance over single large deep neural networks. The idea of considering shallow neural nets as weak learners and constructively combining them started with. In their pioneering work, fully connected, multi-layer perceptrons are trained in a layer-by-layer fashion and added to get a cascade-structured neural net. Their model is not exactly a boosting model, as the final model is a single, multi-layer neural network. In 1990s, ensemble of neural networks got popular as ensemble methods helped to significantly improve the generalization ability of neural nets. Nevertheless, these methods were simply either majority voting for classification tasks, simple averaging, or weighted averaging for regression tasks. After the introduction of adaptive boosting, AdaBoost algorithm, Model 1 input hidden penultimate feat, Model 2, Model K GrowNet architecture. After the first weak learner, each predictor is trained on combined features from original input and penultimate layer features from the previous weak learner. The final output is the weighted sum of outputs from all predictors, where k ranges from 1 to k, alpha k times fkx. Investigated boosting with multi-layer neural networks for a character recognition task and achieved remarkable performance improvement. They extended the work to traditional machine learning tasks with variations of AdaBoost methods where different weighting schemes are explored. The adaptive boosting can be seen as a specific version of the gradient boosting algorithm where a simple exponential loss function is used. In the early 2000s, introduced greedy layer-wise unsupervised training for deep belief nets, DBN. DBN is built upon a layer at a time by utilizing Gibbs sampling to obtain the estimator of the gradient on the log likelihood of restricted Boltzmann machines, RBM, in each layer. The authors expounded this work for continuous inputs and explained its success in attaining high-quality features from image data. They concluded that unsupervised training helped model training by initializing RBM weights in a region close to a good local minimum. Most recently, AdaNet was proposed to adaptively build neural network NN layer by layer from a single layer NN to perform image classification tasks. Besides learning network weights, AdaNet adjusts the network structure, and its growth procedure is reinforced by a theoretical justification. AdaNet optimizes over a generalization bound that consists of empirical risk and complexity of the architecture. Coordinate descent approach is applied to the objective function, and heuristic search, weak learning algorithm, is performed to obtain delta-optimal coordinates. Although the learning process is boosting style, the final model is a single NN whose final output layer is connected to all lower layers. Unlike AdaNet, we train each weak learner in a gradient boosting style, resulting in less entangled training. The final prediction is the weighted sum of all weak learners' output. Our method also renders a unified platform to perform various ML tasks. In recent years, a few works have been done to explain the success of deep residual neural networks with hundreds of layers by showing that they can be decomposed into a collection of many subnetworks. The work extends AdaNet to specifically focus on ResNet architecture to provide a new training algorithm for ResNet. The authors, meanwhile, argue that these deeper layers might serve as a bagging mechanism in a similar spirit to the random forest classifier. These studies challenge the common belief that neural networks are too strong to serve as weak learners for boosting methods. 3. Model. In this section, we describe the basic framework of GrowNet for general loss functions, and then we show how the corrective step is incorporated. The key idea in gradient boosting is to take simple, lower-order models as weak learners and use them as fundamental building blocks to build a powerful, higher-order model by sequential boosting using first- or second-order gradient statistics. We use shallow neural networks, e.g. with 1 or 2 hidden layers, as weak learners in this paper. At each boosting step, we augment the original input features with the output from the penultimate layer of the current iteration. This augmented feature set is then fed as input to train the next weak learner via a boosting mechanism using the current residuals. The final output of the model is a weighted combination of scores from all these sequentially trained models. Gradient boosting neural network GrowNet assumes a dataset with samples in a dimensional feature space D equals xi yi, where xi is in Rd and yi is in R. GrowNet uses k-additive functions to predict the output. For yi equals exi equal k equals 0 to kfk xi, where fk is in F, the space of multilayer perceptrons, and hk is the boost rate. Each fk is an independent, shallow neural network with a linear layer as the output. The model calculates the prediction as a weighted sum of k's in GrowNet for a given sample x. Let L be any differentiable convex loss function. The objective is to learn a set of functions, shallow neural networks, that minimize the equation LE equals 0 to n, Lyi. Regularization terms to penalize model complexity are omitted for simplicity. Traditional optimization techniques won't work as we're optimizing over the functions, not the parameters. Similar to GBDT, the model is trained additively. The output of GrowNet at stage T1 for the sample I is represented as depriswav T-1, T1 to k equals 0, of kfkxi. Next, the model seeks the weak learner ftex that minimizes the loss at stage T, elp T equals x1 n on f plus I. Taylor expansion of the loss function L is used to simplify computational complexity. Models are trained with Newton-Raphson steps for second-order optimization. Model parameters are optimized by running regression on the second-order gradients of GrowNet's outputs. The objective function for the weak learner ft is lt equal to n h high yi minus f of txi forward, where 12 yi equal matted gi high, and gi and high are the first and second-order gradients of the objective function at xi with relation to the y1i. Corrective step CS differs from traditional boosting by allowing the update of parameters of previous weak learners through backpropagation. This dynamic approach avoids local minima and alleviates the issue of a fixed boosting rate. CS acts as a regularizer to reduce correlations among weak learners, focusing on the task-specific loss function on original inputs. The usefulness of CS is further explored in empirical and theoretical investigations. The corrected step is detailed in Algorithm 1 in the supplementary material. Applications of GrowNet include regression, classification, and learning to rank problems. GrowNet for regression. We employ mean-squared error MSE loss function for the regression task. Let us assume the MSE loss, then we can easily obtain yi first-order and second-order statistics at stage T as follows. gi equals 2 y t minus 1 I minus yi, hi equals 2 yi equal yi minus t minus 1 I. We train the next weak learner ft by least square regression on xi yi for I equals 1 to n. In the corrective step, all model parameters in GrowNet are updated again using the MSE loss. GrowNet for classification. For the illustration purposes, let us consider the binary cross-entropy loss function. However, note that any differentiable loss function can be used. Choosing labels yi minus 1, this notation has an advantage of y2i equal 1, which will be used in the derivation. The first and second order gradients, gi and hi, respectively, at stage T can be written as follows. gi equal to 2yi1 plus e2yiy of t minus 1i. hi equals 4y2 i e2yiy 1 plus equal from I of gi 2 equal y minus gi1 of 2y ie1 of t minus 2. The next weak learner ft is by least square regression using the second-order gradient statistics on xi, yi. In the corrective step, parameters of all the added predictive functions are updated by retraining the whole model using the binary cross-entropy loss. This step slightly corrects the weights according to the main objective function of the task at hand, i.e., classification in this case. GrowNet for learning to rank. In this part, we demonstrate how the model is adapted to learning to rank, L2R, with a pairwise loss. In the L2R framework, there are queries and documents associated with each query. A document can be associated with many different queries. Then for each query, the associated documents have relevance scores. Assume for a given query, a pair of documents UI and UJ is chosen. Assume further that we have a feature vector for these documents, XI and XJ. Let Y and YJ denote the output of the model for samples XI and XJ respectively. According to 4, a common pairwise loss for a given query can be formulated as follows. L of yi yj equals 1 2 1 minus sij 2 y minus moh yj plus 1 plus e mith, where sij 0 minus 1 plus 1/12 denotes the document's relevance difference. It is 1 if UI has a relevance score greater than UJ, minus 1 vice versa, and 0 if both documents have been labeled with the same relevance score. Signo is the sigmoid function. Note that the cost function L is symmetric, and its gradients can be easily computed as follows. For the details, readers can refer to 4. Tai YIL, YY YJ equals to signo 1 2 1 minus IJ, minus 1 1 plus E signo, TYI minus YJ, equal minus DYJL, YI EYJ, D2 DYLYJ equals to C2011 plus E signo Y minus YJ, 1 minus 1, where I denotes the set of pairs of indices Q I J J, for which UI is desired to be ranked differently from UJ for a given query. Then for a particular document UI, the loss function and its first and second order statistics can be derived as follows. L equals to JIL TYI YJ plus J JI IL YYJ. GI equal to JIJ I to YI LY YJ minus SUJ JI I to YL YYJ. HI CLI YI Y2 YL JJJI by the 2 YLYJ. Experiment setup. All predictive functions added to the model are multi-layer perceptrons with 2 hidden layers. We generally set the number of hidden layer units to roughly half of or equal to the input feature dimension. More hidden layers degraded the performance as the model starts overfitting. 40 additive functions were employed in the experiments for all 3 tasks, and the number of weak learners in the test time is chosen by the validation results. Boosting rate is initially set to 1 and automatically adjusted during the corrective step. We trained each predictive function for just 1 epoch, and the entire model is also trained for 1 epoch during the corrective step by stochastic gradient descent with Atom Optimizer. Table L2R results in normalized discounted cumulative gain for top 5 and 10 queries on Microsoft Learning to rank with 10K queries and Yahoo LTR datasets. GrowNet results are average of 5 iterations, and the values in the parentheses represents the standard deviation. MSLR Web 10K Yahoo LTR NDC 5, NDCG at 5, NDCG at 10, XG Boost 0.477, 0.0287, 0.4858, 0.0245, 0.7618, 0.7913, GrowNet Pairwise Loss 0.5106, 0.011, 0.5203, 0.015, 7726.06, 0.8101, Ethernet. GrowNet Gen I div loss 0.5044, 0.072, 0.7713, 0.7713, 8088.005 is increased to 2 for the ranking task. We also employed 2D batch normalization on the hidden layers. We compared the model performance with XG Boost, since similar results are obtained with LightGBM or Cat Boost, and with AdaNet. Tuning and model details of all 3 methods are provided in supplementary material. Datasets. We evaluate our model on 5 datasets from 3 different tasks. Higgs boson dataset is used for classification. Higgs data is created using Monte Carlo simulations on high-energy physics events. To perform regression, 2 datasets from UCI Machine Learning repository are selected. The first one is computed tomography CT slice localization data, where the aim is to retrieve the location of CT slices on axial axis. The second regression dataset is year prediction MSD, a subset of million song dataset. The goal is to predict the release year of a song from its audio features. We choose Yahoo LTR dataset for the learning to rank task as it is a well-known benchmark dataset and also used in XGBoost's paper. The dataset has 20K queries each associated with approximately 22 documents. Train test split from the original paper is preserved. The second benchmark ranking dataset we used is MSLR Web 10K, in which there are 10K queries, each corresponding to a list of 100 to 200 documents. Detailed statistics of each dataset can be found in the supplementary material. Results. Regression results in root mean square error, RMSE. GrowNet results are average of 5 iterations, and the values in the parentheses represent standard deviation. Music year pred, slice locals, XGBoost 8.9301 6.6744, AdaNet 12.1778 GrowNet 8.8156 0.061, 5.312.3512 classification results in AUC on Higgs boson dataset. For our model, we preset 3 different results, using all the data, 10% of the data 1M and 1% of the data 100K. XGBoost 0.8304 GrowNet, all data, 0.8510 GrowNet data sampling 10%, 0.8439 GrowNet data sampling 180 regression. Table reports regression performance on 2 UCI datasets. GrowNet outperforms both methods on music dataset, where AdaNet delivers the worst result. On CT slice localization dataset, our model obtains on par results with AdaNet and displays 21% decrease in RMSE compared to XGBoost. Classification. To make a fair comparison with XGBoost, we tested our model on Higgs boson dataset as it is used in XGBoost's paper. Classification results are presented. GrowNet clearly outperforms XGBoost using all the data. Subsampling 10% of the data for training each weak learner also renders better performance. We use 30 weak learners, multi-layer perceptrons with 2 hidden layers of 16 units, and the number of weak learners to be used at test time is chosen by validation results. In all 3 experiments, this number was 30. Learning to rank. Ranking experiment results on Yahoo and MSLR datasets are presented. We evaluated GrowNet with 2 different loss functions, namely pairwise loss and generalized I-divergence loss. In both scenarios, GrowNet outperforms XGBoost on both datasets. In particular, it delivers 6 to 8% increase on Microsoft data in NDCG at 5 and NDCG at 10. For our model to achieve these results, 30 weak learners were enough. Ablation study. Ablation study experiment results on Higgs and Microsoft datasets with 2-layer shallow networks as weak learners. Hidden layer dimensions are 16 for classification and 64 for ranking tasks. The final GrowNet model is compared against different versions. AUC scores for classification and NDCG for ranking are reported. For Higgs dataset, 1 million points were randomly selected for training, with 5% reserved for validation. Original test data used for testing. For Microsoft dataset, fold 1 was preserved. Only the component under analysis was altered while other parameters stayed constant. Ablation experiments are summarized in Table 4 with the results of the final GrowNet model. Stacked versus simple versions were compared. The stacked model utilizes features from the penultimate layer in addition to the original input, resembling auto-context in literature. Stacked model outperforms the simpler version, especially in the ranking task. Training loss also supports the advantage of the stacked version. Unlike tree boosting methods, the model's weak learners allow for this architecture. Analyzing the corrective step, it's deemed vital. This step updates parameters by training the model on original inputs without penultimate layer features. The procedure enables the model to adjust parameters task-specifically. Using the corrective step every 5 stages improved performance compared to not using it at all. However, the performance was not as good as with GrowNet's results. The stair-like loss curve evidently displays the influence of the corrective step on model training. Dynamic boost rate. Within the corrective step, we are able to dynamically update the boost rate alpha at stage T. Taking this measure saved us from tuning one more parameter, as well as yielded a mild performance increase in all tasks. Moreover, the model obtained better training loss convergence compared to the fixed boost rate version. In our setup, starting with alpha 0 equals 1, the boost rate is automatically updated each time the corrective step is executed. Results of the best constant boost rate alpha t equals 0.1, coarsely tuned in a set of 0.01, 0.1, are reported in the 5th column. 6.3 First-order statistics versus second-order statistics. In this experiment, we explored the impact of first and second-order statistics on model performance, as well as on the convergence of training loss. As the 4th column displays, Using the second order renders a slight performance boost over the first order in classification, and almost 2% increase in learning to rank tasks. The effects of first and second order statistics on training loss are shown in the figures. The final model with second order statistics again shows slightly better convergence in classification, yet the difference is more apparent in ranking. As the learning rate is decreased by a rate of 1/2 per 15 weak learners, sudden drops are observed in the classification loss curve at 15th and 30th stages. 6.4. Analyzing the effect of hidden layers. As the literature suggests, boosting algorithms work best with weak learners. Thus, we utilized a shallow neural network with 2 hidden layers as a weak predictor for our model. While adding more hidden layers yields stronger predictors, they are not weak learners anymore. To explore this weak learner limit on the number of hidden layers, we assayed weak learners with 1, 2, 3, and 4 hidden layers. Each hidden layer had 16 units. Although weak learners with more hidden layers render better training loss convergence as expected, the overall model starts saturating in performance and overfitting. Weak learners with 1 and 2 hidden layers attain the best scores, yet the latter one outperforms the former. The worst test AUC score is from the model with 4 hidden layers. Altering the number of hidden units has a lesser effect on performance. To illustrate the impact of hidden layer dimensions, we tested the final model with various hidden units. Higgs data has 28 features, and we tested the model with 2, 4, 8, 16, 32, 64, 128, and 256 hidden units. The smaller the hidden layer dimension is, the less information propagation the weak learners get. On the other hand, having a large number of units also leads to overfitting after a certain point. Test AUC scores from this experiment on Higgs 1M data shows that the highest AUC of 0.8478 is achieved with 128 units, yet the performance suffers when the number is increased to 256. 6.5 GrowNet versus DNN. One might ask what would happen if we just combine all these shallow networks into one deep neural network. There are a couple of issues with this approach. 1. It is very time-consuming to tune the parameters of the DNN, such as the number of hidden layers, the number of units in each hidden layer, the overall architecture, batch normalization, dropout level, and etc. 2. DNNs require a huge computational power and in general run slower. We compared our model against DNN with hidden layer configurations. The best DNN with 10 hidden layers produced 0.8342 on Higgs 1M data in 1,000 epochs, and each epoch took 11 seconds. The DNN achieved this score at epoch 900. GrowNet rendered 0.8401 on the same. Configuration with 30 weak learners. The average stage training time, including the corrective step, took 50 seconds. Both models are run on the same machine with NVIDIA Tesla V100, 16GB GPU. We find that GrowNet has a clear advantage over stacked DNNs on all these aspects. Further details and illustrations from the ablation study and the code are provided in supplementary material. Conclusion. In this work, we propose GrowNet, a novel approach to leverage shallow neural networks as weak learners in a gradient boosting framework. This flexible network structure allows us to perform multiple machine learning tasks under a unified framework while incorporating second-order statistics, corrective step, and dynamic boost rate to remedy the pitfalls of traditional gradient boosting decision tree. Ablation study is conducted to explore the limits of neural networks as weak learners in the boosting paradigm and analyze the effects of each GrowNet component on the model's performance and convergence. We show that the proposed model achieves better performance in regression, classification, and learning to rank on multiple datasets compared to state-of-the-art boosting methods. We further demonstrate that GrowNet is a better alternative to DNNs in these tasks, as it yields better performance, requires less training time, and is much easier to tune. Broader impact. GrowNet describes a novel boosting framework, which could be applied to a wide range of tasks and application domains, not limited to classification, regression, and learning to rank, which are discussed in this paper. Our research could help improve the performance of these tasks and applications in practice. While there are general impacts of our work, similar to those of the popular boosting methods, we focus on the impact of the ease of employing boosted neural networks in practice. The potential benefits are improved predictions in a lesser amount of time, instead of a longer time to comprise application-specific algorithms in a wide range of applications. For example, in healthcare, better predictions result in better diagnosis, which could save lives. In social domains, better predictions improve the quality of our lives. The list of tasks and applications, where our method could be adapted to, goes on. While there are undoubtedly benefits, there are many concerns and risks of irresponsible uses. This is even more important in today's environment, where the issues such as bias, discrimination, privacy, etc. increasingly become more serious. Better predictions should not result in bias and discriminate decisions and invasion of privacy. To mitigate these risks and concerns, we encourage the research community and policymakers to understand and evaluate the specific impacts of more and more powerful, ready-made artificial intelligence algorithms. Here, we need to understand the risks and derive the appropriate policies, but should not hinder research activities when there are clearly beneficial implications. Chappell, O. and Chang, Yahoo Learning to Rank Challenge Overview. Journal of Machine Learning Research, WNCP, 2011. Chen, T. and Gestrin C. XGBoost, a scalable tree boosting system. In Proceedings of the 22nd ACM SIG-CADI International Conference on Knowledge Discovery and Data Mining, 2016. Corta C. Gonzalvo X. Kuznetsov V. Mori M. and Yang S. AdaNet, Adaptive Structural Learning of Artificial Neural Networks. In Proceedings of the 34th International Conference on Machine Learning, 2017. Fahlman S.E. and Lebier C. The Cascade Correlation Learning Architecture. In NIPS, 1990. Freund, Y. Boosting a Weak Learning Algorithm by Majority. Information and Computation, 1995. Friedman J., Hasty T., and Tibshirani R. Additive Logistic Regression, A Statistical View of Boosting. The Annals of Statistics, 2000. Friedman J. H. Greedy Function Approximation, A Gradient Boosting Machine. Annals of Statistics, 2001. Goodfellow I., Pooja Abadi J., Mzu B., Ward Farley D., Ozair S., Corville, and Bengio Y. Generative Adversarial Nets in Advances in Neural Information Processing Systems, 2014. Hansen L. and Solomon P. Neural Network Ensembles, TPAM 1990. He K., Zhang X., Ren S., and Sun J. Deep Residual Learning for Image Recognition in CVPR 2016. Hinton G. E., Osendero S., and Te. A Fast Learning Algorithm for Deep Belief Nets. Neural Computation, 2006. Huang F., Ash J., Langford J., and Shapir R. Learning Deep ResNet Blocks Sequentially Using Boosting Theory. In Proceedings of the 35th International Conference on Machine Learning 2018. KG, Meng, Finley T., Wang T., Chen W., Ma W., Ye Q., and Lu T. Y. Light GBM, a highly efficient gradient boosting decision tree. In NIPS 2017. McKinney S., Sieniak, M. and et al., V. G. International Evaluation of an AI System for Breast Cancer Screening. Nature, 2020. Mogimi M. Ballon J. Siberian M. J. Yang J. Vasconcelos N. and Lee L. J. Boosted Convolutional Neural Networks in BMVC 2016. Opitz D. and Shavlik J. Actively Searching for an Effective Neural Network Ensemble. Connection Science, 1996. Perrone M.P. and Cooper L.N. When Networks Disagree, Ensemble Methods for Hybrid Neural Networks. Chapman and Hall, 1993. Prokorenkova L. Gusev G., Vorobev A., Dorogush A., and Gulin A. Cat Boost, Unbiased Boosting with Categorical Features. In NeurEP 2018. Schwenk H. and Bengio Y. Training Methods for Adaptive Boosting of Neural Networks for Character Recognition. In NIPS 1997. Schwenk H. and Bengio Y. Boosting Neural Networks. Neural Computation 2000. Simeon S., David M., Marco D., and et al. DC. A multimodality test to guide the management of patients with a pancreatic cyst. Science Translational Medicine 2019. 2. Z and by X. Auto-context and its application to high-level vision tasks and 3D brain image segmentation. IEEE Transactions on Pattern Analysis and Machine Intelligence 3010, 1744-757, 2010. Tyree S., Weinberger K., Agrawal K., and Pakin J. Parallel Boosted Regression Trees for Web Search Ranking. In 20th International Conference on World Wide Web 2011. Veit A., Wilbur M., and Belongi S. Residual networks behave like ensembles of relatively shallow networks. In NIPS 2016, Yang Z, Dai Z, Yang Y, Carbonell JG, Salakutinov R., and Lake QV. Excellent generalized autoregressive pre-training for language understanding. In NeurIPS 2019, Zhang F., Du B., and Zhang L. Scene classification via gradient boosting random convolutional network framework. IEEE Transactions on Geoscience and Remote Sensing 54 2016. Zhang T. and Johnson R. Learning nonlinear functions using regularized greedy forest. IEEE Transactions on Pattern Analysis and Machine Intelligence 2014. Zof B., Kubuk E.D., Gyasi G., Lin T.Y., Schlenz J., and Lee Q.V. Learning Data Augmentation Strategies for Object Detection. ArcSieve, ABS 1906.1172 2019. Additional related work. A few works have also been proposed to directly combine gradient boosting with convolutional neural nets, CNN. The authors have proposed to train gradient boosting machine with CNN as a base learner by introducing a custom multi-class softmax loss function for a specific scene classification task in the remote sensing domain. The work on the other hand, focuses on training each CNN sequentially on the mistakes of the previous networks, similar to AdaBoost, to perform on solely image classification task. Our method is different as it is a unified framework to perform various machine learning tasks, such as classification, regression, and even learning to rank. Moreover, unlike those two methods, we leveraged a corrective step to update the previously added predictor parameters and achieved a significant performance boost. Algorithm pseudocode. The pseudocode of training the weak learner is explained in Individual Model Training part of Algorithm 1. The second part of the algorithm describes the corrective step. The code is available at GitHub page ht/git.com/badirli/GrowNet. Algorithm 1 full GrowNet training input f0x equals log n plus n of 0. Training data DTR output GrowNet e fork equals to m. Do part 1 individual model training. Initialize model kx. Calculate st order grad. gi equals yk minus 1. ly tort y I DTR calculate nd order grade. hi equals to 2 y of k minus 1 minus 1 I. Train of k by least square regression on xi gi h high. Add the model fk of x into the GrowNet e. Part 2 corrective step 4 poc equals to t to calculate GrowNet output. Yk k equals km equals im fm nth. Calculate loss from GrowNet L equals nly yki. Update model fm parameters through backpropagation tech k. Update step size k through backpropagation end for additional dataset statistics. We evaluate our model on datasets from different tasks. A brief description of these datasets are presented in Table 5. We used Higgs boson dataset for classification. Higgs data is created using Monte Carlo simulations on high-energy physics events. It is a binary event classification data with attributes. For the regression task, datasets from the UCI machine learning repository are selected. The first one is computed tomography, C-slice localization data, where the aim is to retrieve the location of CT slices on the axial axis. The data was constructed from a set of CT images that were taken from different patients, male, female. The second regression dataset is year prediction MSD data, a subset of million song dataset, from the UCI repository. The goal is to predict the release year of a song from its audio features. The songs are mostly Western, commercial tracks ranging from 2, with a peak in the year S. Datasets used in the experiments and their brief description. The second and third columns marked as N, M represent the number of samples and feature dimension of the dataset, respectively. Task Higgs boson, 10 M samples, 28 feature dimensions, binary classification. Slice localization, 53 K samples, 384 feature dimensions, regression. Year prediction, 550 K samples, 90 feature dimensions, regression. Yahoo LTRC, 473 K samples, 700 feature dimensions, learning to rank. MSLR Web 10K samples, 12 M feature dimensions, learning to rank. We chose the Yahoo LTRC dataset for the learning to rank task as it is a well-known benchmark dataset and is used in the XGBoost paper. This dataset has 20K queries, each associated with approximately 22 documents. Train test split from the original paper is preserved. The second benchmark ranking dataset we used is MSLR Web 10K. The dataset contains 10K queries, each of which corresponds to a list of 100 to 200 documents. Hyperparameters of GrowNet experiment setup. All predictive functions added to the model are multi-layer perceptrons with 2 hidden layers. More hidden layers degraded the performance as the model starts overfitting. We generally set the number of hidden layer units to roughly a third of, a half of, or equal to the input feature dimension. 40 additive functions were employed in the experiments for all three tasks, and the number of weak predictors in test time is chosen by the validation results. From all the experiments, we observed that 30 weak learners are more than enough to get the best results before the model's performance saturates. Early stopping or other heuristics can also be incorporated into the model to terminate the training before the model begins to overfit. The boosting rate is initially set to 1 and automatically adjusted during the corrective step. Depending on the dataset and the task at hand, it may be initially set to a lower number, such as 0.1. In our experiments, we did not tune or alter the boost rate. We trained each predictive function for just one epoch, and the entire model is also trained for one epoch during the corrective step using stochastic gradient descent with the atom optimizer. The atom optimizer is run with L2 regularization at a rate of 0.01. Epoch numbers are increased to 2 for the ranking task, as we used larger batch sizes. Increasing the epoch number does not contribute to the performance, and higher numbers cause overfitting. We also performed batch normalization for the hidden layers. The batch size for classification was set to 2048, and the learning rate was set to 0.005. ReLU was used as the activation function for the penultimate layer, whereas leaky ReLU was used for the hidden layers. For the ranking task, we replaced ReLU with ReLU6. XGBoost and AdaNet tuning, XGBoost tuning. For XGBoost, we tuned the main parameters, including the number of trees, learning rate, maximum leaves, and L2 regularization in the following range. Number of trees, 64, 128, 256, 512,000. Learning rate, 0.05. 0.1 maximum number of leaves, 128, 256, 512. L2 regularization lambda 2. GrowNet AdaNet XGBoost AUC 0.8401, 0.8143, or 0.8304 classification results on Higgs 1M data. The scores are in AUC RAC. GrowNet 1HL, GrowNet 2HL, GrowNet 3H, GrowNet 4HL, AUC 0.8288, 0.8401, 0.8146, 0.7801. Results from hidden layer experiment. We did not tune XGBoost on Yahoo LTR and Higgs datasets as we used the results reported in the original XGBoost paper. AdaNet tuning. We tuned three main parameters for AdaNet: the learning rate, the number of subnetworks, and the complexity regularization parameter. Learning rate 0.011, 0.0001. AdaNet iterations have subnetworks 2, 3, 4. Complexity regularizer Lego 0.01, 0.001, 0.001. The model was first tuned with default mixture weights and lig equals 0, as suggested in the author's GitHub page. From this experiment, we got the optimal learning rate and number of subnetworks. Then, using the learned parameters from the previous setting, AdaNet is again tuned to learn the mixture weights and regularization complexity parameter LELR. The model is trained for 30,000 epochs, and the number of neurons in layers is set to 512, following the results from AdaNet paper. We also observed that the model with 512 neurons generally renders better performance. Classification on Higgs 1M. Following the same data split on Higgs data from the XGBoost paper, we created Higgs 1M data. AUC scores on Higgs 1M data from GrowNet, AdaNet, and XGBoost are reported in Table 6. GrowNet renders favorable results compared to XGBoost, and 3% increase over AdaNet result. Additional illustrations for ablation study. Analogous to Figure 2 from the main text, Figure 5 presents pairwise losses on Microsoft dataset from the ranking task. Effect of hidden layers. Results from the hidden layer experiment. GrowNet final, employing weak learners with 2 hidden layers, got the best performance. AUC score is 0.401. The model with a shallow network of 1 hidden layer as a weak learner obtains better performance. AUC of 0.8336. Once the number of hidden units is increased from 16 to 32. The inverse effect on the model with weak learners of 3 or 4 hidden layers did not work as expected. Details on DNN versus GrowNet. Both deep neural network, DNN models, and GrowNet are run on the same machine with NVIDIA Tesla V100 16GB GPU. Unlike GrowNet, DNN performed better with CILU activation functions. We also applied batch normalization on the hidden layers of DNN. Each of DNN models run for 1,000 epochs. The results are reported in Table 8. The best performing DNN model has 10 hidden layers. Training loss visualization for the learning to rank task on MSLR dataset. We used pairwise loss. Classification training loss, classification test loss. Effect of hidden layers on model training and classification performance, AUC. Approximately 12 seconds. The model reaches its best performance after epoch 900. GrowNet shows a clear advantage on both classification performance and training time. Both methods, DNN and GrowNet, are not fully optimized, thus their training time can slightly be improved. Displays the training time of GrowNet while adding new weak learners. DNN with 30 hidden layers are implemented with dropout 0.3. As without dropout, the model started to overfit immediately after a few epochs. That also explains very close training times of DNN with 20 and 30 layers. Models DNN5, DNN10, DNN20, DNN30. GrowNet training time sec 10, 11, 15, 50, AUC 0.8288, 0.8342, 0.838301, 0.8401. Training time and performance comparison between DNN and GrowNet on HIG1M data. Training time for DNNs are average seconds per epoch, and for GrowNet, average seconds per stages. Training time over iterations is linearly correlated with the number of weak learners.